you have this special symmetry here where this element is in, I guess it's like the stabilizer or maybe centralizer. I don't remember.
I avoid these words because nobody can remember what I mean. Let me just say what the groups are. So the groups are, in the crystallography, there is a group called P1, and that's just infinite cyclic group. So what it is you have a tile, it's a fish pointing in one direction, for example, no reflection. And I tile my one-dimensional floor, infinite floor, with a fish just looking to the right. Its symmetry is cyclic group C infinity, and it consists of all translations, infinitely many, equation 113.
Sorry, why do they call this a separate group? Isn't this just Z?
You're free to call it that, but if you're a group theorist, Z is like inconvenient notation when the real notion is cyclic group.
Yeah, so this is just
and Z modulo N is a cyclic group.
Yeah, well,
but
so
cyclic group is C for cyclic, while Z is God knows what.
Oh,
so in group theory, these things are called cyclic dihedral groups, etc.
Maybe
in
this
finite group theory. Yeah.
There's a difference in like notation. What I was taught was that cyclic means
in your book, damn it, it's called CN.
Yeah, I know. I'm just saying.
So yeah.
From what I was taught is just means generated by a single element. So Z is cyclic.
C infinity means that it generates a single element, but there is no any other condition.
Right.
The CN says this stops, makes it a finite group. When you enumerate space groups in crystallography, what you're doing is they all have translation. And depending on dimension, they're translationally invariant in D dimensions if you have D-dimensional lattice. So translations always form the normal subgroup of the space group. Now, what is a space group? It's a group of all admissible translations and rotations. On lattices, translations are digitized, They're basically only 5 possible discrete rotations you can have. You can rotate by 180 degrees, by 90 degrees, by 30 degrees, and you cannot rotate by 2 pi over 5. If you do that, you get a Nobel Prize because you invent quasi-crystals, but you cannot do it. Not in the classical crystallography until 50 years ago. So then you have to classify them in 3 dimensions. That's a classical crystallography. In 2 dimensions, you classify them. They're called wallpaper groups because you can draw beautiful pictures. And 1 dimension is very boring because there are only 2 space groups. There's a group of no rotation, that's the cyclic group. And only rotation on the line is by 180 degrees. And that group is called P1M in crystallographic notation. Or in mathematics of people who do finite groups but have forgotten their abstract algebra courses, it's called dihedral group or infinite dihedral group. So that's in Wikipedia, so that's as good as gold. Okay, so there, in 1 dimension, there are only 2 possible theories you can write. Their symmetries are either cyclic or dihedral. That's all you can do. And that happens to match very nicely with everything we know about dynamical systems, because either you can march in one direction, that's dissipative flows, or you can suffer and have a whole seminar on symplectic surgeries, etc. if you do the other possibility, which is you have time reflection. But in 1 dimension, that's all. In discrete 1 dimension, that's all there is. So the dihedral group has all the rotations in it, but then it has the reflection elements, the same number of them, and they have a property that you move k steps, the equation 114, you move k steps forward, and then you flip.
Mm-hmm.
And that means you flip not right at the origin, but at some k site away from you.
Mm-hmm.
And the amazing thing is that you discover there are two classes. The even one, I stand here and I flip, is different from odd ones. I move by odd number of steps and flip. And the multiplication table is simplicity itself. Multiplication table says rotations add up, but rotation times a flip sends me backwards. And if I flip twice, I get a rotation. Now the subgroups are all infinite, interesting subgroups. There could be cyclic groups that are infinite, but they jump in steps of length. That's called Bravais lattice, or they jump in steps of the size of the cell, basic Bravais cell.
Mm-hmm.
So they are nice subgroups of both cyclic and dihedral group. And then you have another set where you jump in steps of R, but you flip in steps of K times R. So I don't flip at the origin, but I flip someplace else. Each one of them is a subgroup.
Mm-hmm.
And now the question is, what's the index? These are all subgroups. So what indices these subgroups have? And I've proven to you what the indices are by showing you several pictures. So I don't need to talk about cardinality and any other such thing. That's how you compute the index.
So just to be clear though, so the way that this would normally work when you're like trying to build a field theory, right, is like you would start off with an infinite dimensional lattice, and then you would say, my theory is going to have this as a symmetry group.
And then there are lots of things that happen. Working on reciprocal lattice is beautiful. This is what all physicists and crystallographers and chemists do. Nobody in dynamical systems does it, but we should. I mean, Hill and Poincaré did it originally, but it's not how we do it.